Okay, I think that we can start our class, this Friday class, with some more details on the estimate of the model parameters. We saw basically two approaches that were dealing with the multi-layer freedom system approach and basis, sorry, and both of them are using what is called the stabilization diagram. And according to the different choice of the model order, and for example, these algorithms, not only those that we consider, but also all the set of algorithms that are based on the multi-layer freedom system hypothesis, are finding the different poles corresponding to the different model orders. And it is you as the experimental engineer that you have to choose between those sets of poles. And therefore, in order to have that, we are defining this stabilization diagram with the information concerning the imaginary part of your poles, just identified poles, and we compare this imaginary part or the real and imaginary part all together in order to find out the stabilization of the pole that we are considering. The reason why not that is that, of course, the pole of a system is not depending on the model order itself. There are a number that is dependent on the model order, but the pole itself is not dependent at all from the model order, that, as you can see from the basic equation. And so the way you can estimate your model parameters is just finding what is called the stable poles. Okay, the stable poles that are generally referred to as an S. This S is representing the fact that the poles, when moving from one model order to the next one, is not changing that much. In order to characterize these changes, we are here these definitions for the pole identification in the stabilization diagram. So when we are referring to the O, that is that circle that we are having in that plot, we are just referring to these just identify pole. Okay, and that comes from the numerical methods that we are considering. That could be the complex exponential method, that could be Ibrahim time domain method, could be whatever. Okay, then the next name that we are giving to the pole is an F stable pole, that is a pole stable in frequency. That is that if you consider the natural frequency that we are considering at the ith, okay, model order, and we compare that with the previous I-1 model order, the difference in amplitude is less than a prescribed small quantity that is representing the stable in the frequency. Okay, so that is the I model order, and that is the estimated natural frequency. Okay, then as you can see from the plot, we are also having what is called the D-stable pole. That is your pole stable in damping. That is, we are saying that the corresponding zeta coefficient damping ratio at the ith model order compared to the corresponding damping ratio at the ith negative one, so the previous model order, is once again less than a prescribed value that is referred for the zeta, for the damping ratio. Then what we got is a V pole, that is a pole stable as vector or complex. Okay, what does it mean that? It means that we are demanding more strict conditions for the stability. Okay, that means that if you consider the pole, a complex pole evaluated at the ith model order, and you compare that corresponding at the previous model order, and then you take that as the amplitudes of these two, then this is a very small quantity. Okay. Finally, we have the stable pole, and we consider that as stable when we are going to have more stricter conditions than the previous one. That is, we have to characterize both the real and imaginary part. So in our analysis, you consider the real part of the pole at the ith model order, then you compare that with the previous model order, like that, and this should be less than the prescribed quantity, for example, S, and together, okay, the imaginary part, the same. Okay, so that is the way we are finding, or better, we are estimating your modal parameters starting from the estimate of your poles in the stabilization diagram. Okay, so that's the reason why we are generally referring to this process as an estimating process, because as you can see, and going back to a typical plot like the one that you are seeing right now, you can have a number of stable poles once you reach the, let's say, good or acceptable model order. Just have a look to the first peak of resonance. We are starting, for example, by the lower circle that we are having, then we find out an F, then one O, once again, then F, D, V, and then we have a set of stable poles S. So it's up to you choosing the best S. Okay, those S's are all referring to a very stable pole because they are having both the real and imaginary part that are not changing by changing the model order. So the stricter conditions then the previous condition for the stability of the poles, okay? But of course, when you are talking about the corresponding residual terms, then you have to see what's happening. So that's the reason why you have to take an estimate of that. Just because I'm talking about the residual term, please consider that once we estimate the poles, remember we can have the information of the model parameters from the response model, from the frequency response function, just by relating the two conditions, representation using this very well formula. So now it is a summation sign from k that goes to 1 to m, that is your modal order, and then you have the residual terms corresponding to the ij degrees of freedom found out by your FRF pairs and corresponding k's contribution, and then you have j omega negative lambda k plus the complex and conjugate part. Okay, so aij complex and conjugate referring to the same kth mode, and then j omega negative lambda k complex and conjugate. Okay, we didn't prove that, but I already informed you that these residual terms are all related to the Bose shapes by this relation. Okay, a I j k mode is equal to whatever a constant, that is an arbitrary complex complex constant that is scaling your mode, and then your psi I k, psi j k. Okay, so this is the relation between the residual terms. If we can consider that your psi whatever mode, so if your k mode is a real one, then we can say that your complex quantity ak is given you by 1 over 2j and k omega t k. Okay. Now, having said that, we can now have a discussion on how to estimate your mode shapes from your experimental investigation, from your estimate by using whatever approach, okay? Because once you find out your stable pole for your stabilization diagram, you can also go back to the estimated FRF using H1 and H2 estimator, and then by plugging that value of the pole into the equation, it is just a matter of evaluating the residual terms, and those residual terms are related to the mode shapes in the way that we are considering right now. But now, because of the definitions, what we are having is that for each I and j degree of freedom, okay, we're referring to the residual term that once again is written as this. Divided by 2g omega e k and k. Okay, so because of that, we are having a number of m equations where m is the number of modes that we are considering, but we are having m plus 1 unknowns. Okay, and these are given you by the m participation factors. This is your mode shapes plus your modal mass. Okay, so once again, going back here, whatever method we are using in a multi-degree of freedom system under the multi-degree of freedom system hypothesis, we end up with that stabilization diagram. That stabilization diagram is very useful, and indeed it is used to estimate your pole following the stabilization process. What does it mean? That we are estimating the poles of the system corresponding practically to each peak of resonance by choosing the poles that are stable. What does it mean stable? Following the process, we are having the O, F, D, V, and finally S table. That is that we are choosing the poles that are not changing that much with respect to the change to an increase of the modal order. Okay. Once we got that, and that is up to you to choose that, and that is your estimation process, then you can also estimate the mode shapes, okay, from that knowledge and from the measurement of your Hij, okay? What does it mean that? By considering that equation, typical relation between the response and the modal model, now we know the left-hand side because we know the FRF, we know the poles because we have just estimated your lambda k. So what we have to see now is what we have to find out is the residual terms, and those residual terms are related to the mode shapes you considering, and that is visible from that equation that I've just written. Now, because of that, we have also to include the scaling factors, because we are having a number of equations that is less than the number of unknowns, because we have also to include the modal mass in addition to the mode shapes component at the Ij degrees of freedom. Okay, so how we can do that? Yes, what we are doing is just choosing the scaling approach that we would like to follow. Okay, you know, most shapes are all defined unless one unknown constant. From the experimental point of view, here we are. Now we are choosing our scaling constant. Okay, how we can do that? Just remember the information of the residual terms, okay, in terms of the model parameters. So we can have first choice is unitary model mass, and that means that we have to find out your modes, your K modes, so that we are choosing mk equal to 1. Go back to the previous equation, okay? Here, now we are setting mk equal to 1. You know the left-hand side because you know the residual terms, and therefore you have all the equation to find out all the mode components. Okay, that is your first choice. Second choice is, for example, unitary modal stiffness. That means, once again, that you are evaluating your case component, your component of the K mode, sorry, so that your modal stiffness associated to the K mode, that is equal to omega K square and K is equal to 1. Okay? And therefore, once again, we are having the information or the information to find out the components of your case mode. Third condition, the unitary model A it is really called as is model A because we are choosing all the components of your case mode so that your AK that we have just defined is equal to 1. That is another option. Then what we got, a different option could be unitary length. Okay, and in this case, what we are having is your case mode shape so that all the components, okay, from 1 to the number of outputs of your phi I relative to the case mode square is equal to 1. Okay, so we are having the node of that vector that is equal to 1. Okay, or we can also have another choice that could be the unitary maximum modal displacement. Okay, and that is once again your mode shapes is so that we have the maximum of your whatever component of your case mode in amplitude is equal to 1. Okay, and therefore we have another criteria for setting our scaling condition. Okay, so that is what we can have when referring to the monoparameter estimate. We saw some methods. All these methods refer to either a single degree freedom approach or multi-degree freedom system approach. Sometimes there is a connection between these two approaches, and they operate in both in time and the frequency. We saw some methods. Please know that there are other approaches that are available in literature, but however, the basic ones are those that we covered together. Sometimes, and better, most of the times, when we are referring to these multi-degree freedom system methods, we are always referring to that stabilization diagram that is helping you in estimating your poles. We already discussed that. So we use the stabilization diagram to estimate your poles. Once you estimated that, the methods mainly, instead of using the residuals that we have using the considered method, we prefer to estimate your residual terms in a sort of least square conditions equations, or using the information straight from this estimate, just identify estimate of the poles. And in order to do that, we are let's say scaling your Moe shapes in different way, and this scaling options is giving you the corresponding modal parameters, Moe shapes, sorry, cave Moe shapes. Okay, now that's it for this topic. Now, what I would like to start with you is the comparison between the numerical model and the just identified experimental. Okay. Just to remark this topic that is very, very important, please consider that from the experimental investigation, okay, what we can have, as you already know, is the information of the system response. Oh, system response, okay, FRF. Okay, response model, if you remember, response. And from these frequency response functions, through some estimating technique that we consider, we are ending up with our model. Okay, and that is the path from the experimental point of view that is telling you what are the model parameters of your system. From the numerical analysis, we have a quite little bit different okay path. So from numerical analysis, what we are having is your mass, your damping, and your stiffness matrix. Remember, that is your space model. Okay, and therefore from this space model, from numerical solvers, like, let's say, in a finite element modeling, you can consider the MSE Nastran, for example. Then what we got is, once again, your model. By the way, we can say that in this procedure, there are no issues, generally speaking. Okay, there are some numerical issues, but they are always solved, and we know that. However, here in the estimating techniques, there could be some estimation issues, and that is more critical, of course. Okay, and so how can you say that your let's say numerical model is truly representative of your actual experimental structure or system? Then you have to compare these two. Okay, and therefore you can compare these two, okay, for numerical experimental comparison that leads to numerical assessment. Okay. Once you have experimentally validated or assessed numerical model, then you are a very rich person because, or your company is very rich because your numerical model is able to predict whatever responses, whatever structure modifications, so that you can save a lot of time and money just avoiding a very huge number of testing, experimental testing, to be sure that everything is in place after your change, after your numerical, after your, sorry, the structure modification. Okay. Sometimes that is not always true, but sometimes from the model, the numerical model, it is always possible to consider the response model okay, and sometimes we can also compare your response model from the experimental point of view and from the numerical point of view. Okay. So new techniques can validate numerical models using FREFs. Okay, and that is quite new. So generally, the numerical model is validated from the comparison of the model parameters, standard technique. Okay, and this is new technique. Okay, now let's see how we can compare modes. Okay, so preliminary assessment. I'm talking about the assessment of the numerical model to be sure that you are not forgetting this. Okay, is done at the natural frequency level. Okay, so in order to present this preliminary assessment, we have just to consider the difference between the actual experimental natural frequency set and the predicted numerical one. Okay, so the information that we can have that is an error in percentage sometimes that are giving us the information of how far or how close is your numerical model with respect to the experimental investigation. Okay, instead of, so we can say that the error, natural frequency error natural frequency error, okay, that are generally represented as delta natural frequencies, generally compare to the reference one, so they are given in a percentage representation. But instead of using just this information, we are plotting the natural frequency. So the comparison between the natural frequencies is done, let's say, trying to find out the most of these comparisons. And for example, when referring to this plot in which I put on the x-axis the experimental, for example, natural frequencies, and the numerical natural frequencies on the y-axis, what is expected is that if the two models are the same, what could be the final plot? Can you answer to that? So once again, the question is, if I'm comparing the numerical and experimental one, and I am considering this plot in which I put the natural frequency, numerical and experimental one in this picture, what will be the good plot that we are expecting?
Una retta?
Yes, a straight line. Can you say also what is the slope of this straight line? Say again.
1.
45 degrees. Yes, 1.
Yeah.
Okay. Yes. So, for example, we can have a straight line that is your 45 degrees slope, or the coefficient equal to 1. And, for example, if we are having the frequencies like that, 1, 2, 3, 1, 2, 3, okay, those frequencies will align on this straight axis like the one, okay, and that is your perfect correlation. Okay, sorry, that is the line of the perfect correlation. Okay, however, that is not what we are having in real life, because maybe we can have something like this, some other, let's say, like that, and so far and so on. Okay, so what is happening is that we are having a deviation, okay, from the ideal condition, that is the slope 45 degrees, okay, and so what we can say from that is not only the random error, okay, but also we can have information of a systematic error. What does it mean that? Let's assume, for example, that maybe when you are referring to your cantilever beam of your first laboratory activity, you are, let's say, wrong with the estimate of your Young modulus. That means, for example, that your numerical frequencies are a little bit higher or a little bit lower with respect to the experimental one. And therefore, for example, if you are having your natural frequencies that are aligned with respect to a different slope line, okay, like this, for example, then the slope that is different to 45 degrees is a measure of a systematic error. Okay, so if you got this kind of results, then you are very happy because you can see at the very first sight what are the changes that you have to consider in your numerical model in order to have a better match with the experimental results. Okay, so for example, if you are having that slope, this new line, because the experimental natural frequencies are generally higher with respect to the corresponding natural frequency. That means, for example, that your Young modulus is lower than expected, or, for example, the mass is density with mass, for example, is higher than the experimental one. And therefore, you have to go back and talk with your numerical friends and then try to find out a way to introduce this new information concerning the general properties, okay, in your numerical model. That's not it, because you can also redo the same analysis when referring your more shapes, okay? So also more shapes are compared, and that is done in a plot like this, for example. Once again, I am referring to the y-axis. In the x-axis, I'm putting the components of the K experimental mode shape, and in the y-axis, I am putting the corresponding component of the same K numerical mode shape. Okay, maybe for this kind of plot, we have a condition like that. For example, let me add some points like this. Okay, for this comparison, there are not any expected lines, okay, because the mode shapes could be telling me the same information in terms of direction, but having all different components, as we can see from this picture. But however, all those components could be aligned in a sort of, let's say, regression lines, okay, line. And therefore, if the comparison is telling me a plot like the one that I got, that is a component that is aligned with this corresponding one, for example this, okay, and then for example that, oh sorry, okay, that means that we are in a good comparison, in a good correlation, excellent correlation, if all are aligned. So if all the modes, if all the mode components are aligned in a straight line, then we have a perfect correlation. Okay. On the contrary, we can have some condition like this, for example, and therefore we have to consider the deviation, okay, why those mode shape components deviate from, oh sorry, okay, from the perfect line. So maybe there are some parts of the structures corresponding to those components that deviate from the perfect line that requires additional analysis. Maybe locally there are some components that needs a better definition of the mass and the stiffness properties in terms of distributions, in terms of the values. I don't know, but maybe there could be something that have to be considered. Okay, so that is how we can generally preliminary check the correlation between your numerical models and your experimental ones. Another way to compare these two models is, for example, the check for orthogonality condition. Okay, remember, I am considering the comparison between numerical and experimental one, and therefore I know my mass or stiffness matrix. So what is generally done is that we consider that your whatever, let me call that the phi matrix from the experimental analysis transport times your mass model, okay, that is from your numerical analysis, times your phi model, once again, from the experimental investigation, that is equal to the unitary matrix, okay, and that is your experimental unitary matrix, okay. That's because if we are having the perfect correlation, that is just a unitary matrix. If not, then we have to consider that a good correlation could be considered if the numerical and experimental models are if your diagonal terms of this experimental matrix, sorry, okay, experimental sorry, I have to take the charger. 1 second. All right. So, so the unitary experimental matrix is a good one if the diagonal terms are larger than 0.95, and not only that, but the off diagonal terms, okay, are less than 0.05. Okay, what does it mean that if I am having the the right model parameters, the right mode shape, then these mode shapes are perfect agreement with the numerical ones. And therefore, if you consider your numerical one mass matrix compared with the experimental mode shapes, what we are having is just a unitary matrix. If not, we are accepting a good model if there is a 5% in correlation, okay, at least a 5% in correlation, okay. By the way, because we are not having the number of the experimental degrees of freedom is generally less than the numerical ones, then we can refer to a reduced mass model or reduced space model from the numerical analysis, and therefore we can introduce what I call a NR matrix, a reduced mass model. Reduce mass from numerical. Okay, and therefore we can recompute the same experimental unitary matrix just by considering once again your experimental model matrix transpose times your reduced model matrix times your once again experimental model matrix, and that is still the same. Okay, sorry, experimental one. Okay, good. Please note that the mass matrix is, of course, required for this comparison. Okay, so once again, how can I use the result of this comparison in terms of modal mass? Is the if, for example, there is a specific diagonal term that is not, let's say, at least 95 percent, that is not unitary but is a little bit less than 95.95, then that means that the modal mass of the mode is not correctly evaluated, and therefore we have to go back to your numerical model and try to understand why that mode is not well identified from the experimental point of view. And therefore, once again, we have to review some mass or stiffness distribution that is particularly important for that kind of motion, for the kind of motion. Okay, and therefore the numerical process, we start the analysis and then we make the correlation once again. So in order to have a preliminary analysis of your experimental investigation, of your numerical model, sorry, with respect to your experimental investigation, what we are doing is just first a comparison between natural frequencies, not just a percentage error, but evaluation if there is a random error or a systematic error. The random error is given you by the deviation between the straight line of your points in this numerical experimental natural frequency plane, whereas the systematic error is representing the slope of the, let's say, regression line. If that slope is not equal to 45 degrees, then that means that there is a systematic error, and therefore you have to take action in order to reduce that systematic error. Okay. Always from the preliminary point of view, we can compare using the same approach, the mode shapes. Okay, so you, in the plane in which you put the components of the experimental and numerical modes, all these components should be aligned in a straight line if those modes are telling the same thing, that is, if those modes are parallel. Okay, if not, you have to see what are the components in which there is the most of this deviation between the linear gradation between these two modes, and therefore take once again action in your numerical model to see why those mode components deviate from linearities, and therefore you have to redistribute or recheck the general properties of your numerical model according to those degrees of freedom. Finally, you can, because you know the numerical mass, you can check for the orthogonality conditions. Therefore, you can use the modal mass, the experimental modal mass, and therefore you project that modal masses into experimental. Sorry, you can have them. I made a mistake. You can use the experimental mode shape matrix, okay, with the numerical mass matrix in order to see if there are the conditions for an experimental unitary matrix that are met. Okay, what does it mean? That it means that your diagonal components of this identity matrix should be at least larger than 95.95. The off-diagonal terms are should be less than 0.5. That's to be sure that your orthogonality conditions are all satisfied. Sometimes, most of the times better, the degrees of freedom, experimental degrees of freedom are lower than the numerical one, and therefore, by using some numerical techniques, we can reduce your mass model, numerical mass model, to the experimental degrees of freedom, and therefore you have to consider your reduced mass, as I wrote just before, in order to evaluate your experimental identity matrix. Once again, if you are noticing that some points in this experimental unitary identity experimental matrix is not unitary, but they are deviating a lot with respect to unitary, then you have to check why that mode shape, that is, why that modal masses is that different with respect to the one that is expected. Okay. So that's it for today. Thank you for your attention. Any questions? Okay, so if there are no questions, I thank you very much. I wish you a great weekend. See you.